But I'm starting recording anyway. Okay. So. I know we have a lot of late passes, so Phil Simon's gonna be coming in as late as possible. So. The last day to turn in anything. Is. Friday, May 12th. Final grades must be submitted in SOAR by the morning of May 15th. I need a weekend to get all the grades sorted. Now, what I'm going to do is, so after Friday passes, so after 11:59 p.m., so it's the next day. It's something that Dr. Chapman, who helps coordinate all the Lumen sites, let us, all the instructors know about. We use the Lumen system. Any grades, anything that's not been submitted, I will have to make sure the grades computed correctly. I'll be entering a 0 for. So make sure you get in anything you can, and you make use of all your late passes and to avoid having any zeros. Now, I will drop most homework and most goods. I will not drop the lowest test. That's a bridge too far. Now, Canvas is not wired right now to drop the lowest because it would artificially inflate your homework and quiz grades. I'll implement that rule in Canvas over the weekend. So I'll try to make it so that once the final exam grades are entered and any last assignments come in, that my goal is that what you see in Canvas will be an accurate reflection of every grade. Because sometimes it happens to other students where they see something in Canvas, they figure getting a certain letter grade, and then they're not getting it. And I brought it up at a faculty meeting, and my colleagues were like, "Oh, let's just not show grades in Canvas then." Like, oh, that's not the solution. That's not why I brought this up. But okay.
That's what they did in the lab. They just don't put grades in Canvas anymore.
I honestly thought we were required to. During the pandemic, we were definitely required to. And I wasn't aware of that changing, so it's I don't know, but I try to have more transparency about these things. I don't want there to be surprised. As far as the cutoffs for letter grades, because I mean all you're going to see in Canvas is your numerical grade. So I generally use straight scale cutoffs, and I do round up. So in other words, if you see in Canvas that you have an 89.5 and up, that would be considered an A, and so on. In some cases, I may make the cutoffs a little more generous. It depends on where the grades fall, but at least that way you have a lower bound as to what your letter grade will be. The final was held early in finals week, although that might not be best for you all. But at least that way I can have everything graded well before all the I'll try to get those graded within those couple days after the final happens, so that by the time you get to the end of the week and you've turned in everything that's still outstanding, that you'll have an idea of where you're at. Okay. So, yeah, I think it's everything I was administrative that I needed to go through. So otherwise, the purpose of today is just to take any questions you may have about the final practice, the solution, anything in that area.
The conic section is a testimony.
It will not be there.
I just wanted you to work number 2 on these practice because I just don't really do that very well.
Which one?
The ship moving northwest.
Right, okay. Yes, and there will be a ship passenger problem on the final, just different particulars like direction or speed.
Same problem, but with the opposite, what's it called? The opposite like direction. Just to see what it does,
Oh, okay.
like a variation of the problem.
All right. I'll do something different. Okay, but well, first I'll show the actual one. Okay. Okay. So you have ship move northwest. We'll call that vector. That's at 50 miles an hour. And then on the ship, you have a passenger who's walking on the deck, going southeast. I'll call it vector P, and going 4 miles an hour. So the question asks, find the speed of a passenger relative to the surface of the water. So in other words, taking both the movement of the passenger's own movement and the movement of a ship into account. And then as a bonus, find the passenger's direction as an angle. I mentioned that 0 degrees is due east. I don't actually care if the angles and degrees or radians. I'm gonna have both worked out in my solution anyway. Okay, so the idea is you're going to add these vectors. And then the magnitude of that vector, so let's R, the resultant is going to be E plus S, so then the speed is going to be the magnitude of R. So that's the main part of the question. And then for the bonus, and if R has components, we'll call them Rx and Ry, then the direction as an angle, tan theta is equal to Ry over Rx. So those are your formulas that you'll need for this problem. But in order to perform the addition, you need the components of the vectors for the ship and the passenger. So for the ship, you're gonna have the magnitude of 50 and then components corresponding to the angle based on its direction. So the direction is northeast. So the angle is going to be, what is going to be the angle for going northeast? If 0 degrees is east, so the
It would be
Possibly.
135.
yeah, 135 degrees or 3 pi over 4. Okay. All right. And then for the passenger, the magnitude of 4 and cosine and sine of that angle. So what is going to be the angle for whoops, that's northwest. I bet
350.
I would say
350 degrees.
Okay, so 350 degrees, also known as 7 pi over 4 radians or minus pi over 4. Okay. Apologize if I've been saying northeast before, northwest. Sorry, I am functioning on 3 hours of sleep.
I think we all are.
Yeah.
I mean, I can see the arrow up there. and
Yeah. Yeah. Okay. All right, so now you have a components. So now you can go ahead. And then add it, well, actually. Okay, I'll write over here, working out cosine and sine of these angles. So for a ship, we're gonna have, so cosine of 3 pi/4 is minus square root of 2/2. And then sine is positive square root of 2/2. And then for the passenger going southeast, it's gonna be the opposite. So we have 4 times square root of 2/2. And 4 minus square root of 2/2, because you're going the opposite direction. So you're just gonna negate the cosine and sine from the other one. Okay, so now you go ahead and add corresponding x components and y components. So you're gonna have okay, works out to be minus 23 square root of 2 for the x component. But I have 15 minus 4 is 46 divided by 2. So it's going to be plus 23 square root of 2 for the y component. Any questions on just getting the resultant vector?
And so getting the direction, we would do the thing where we take Ry for Rx and then the inverse tangent. But because the x is negative, we would add pi. right?
Yes.
Okay.
Yeah. Oh. What about the speed? What's the speed going to be in this case?
46.
Yeah, so we're gonna have square root of 3 squared times 2 plus 3 squared times 2. So that works out nicely to be 46 miles per hour. And then for the direction. So the two components are negatives of each other. So in this case, tangent theta is equal to -1. So theta is equal to inverse tangent of -1. And then because, as mentioned earlier, the x component is negative, you have to add pi if you're dealing in radians. What is the inverse tangent of -1?
Pi/4.
Negative pi/4.
Minus pi.
Negative pi/4. It's
Yeah.
easy, yeah.
Yeah, tangent's not function. So -pi/4 plus pi is 3 pi/4, which is northwest. So, so really what's happening is, passengers walking towards the back of a ship, aft, I guess. I don't know this term. And, but relative to surface of water, they're moving, with the ship just at a, slightly lower speed because they're walking towards the aft. Oh. That looks like an X, it's supposed to be a plus. Okay, all right. Questions on how that one worked out?
On the exam, if they are if the directions are complete opposites of each other.
Yeah.
Can we not just directly subtract or add the vectors
That does work, so yes.
rather than doing all that, save a little bit of time?
Yeah, but, it's not gonna happen.
Okay.
But if it did, then yes, you could. Yeah, because I want to show the process that works in general. And on request, a variation let's have the passenger moving in a different direction. What if? What if they're heading to the north, and it's still at 4 miles an hour? So. Okay, so in that case, he's just gonna be, the doing bottom of cosine and sine, for the x component is definitely 0. And then the y component is gonna be +4. Okay, so now you're gonna add that to your, to the ship's vector. So, we're gonna have for the x component, we're just gonna take the x component from the ship's vector, so -25 times square root of 2. And then 25 square root of 2 from the ship, for the y component, +4. So things don't work out quite as nicely. So the magnitude of r will be square root of 2 squared plus 1 square root of 2 plus 4, the whole thing squared. Okay. So we end up with, oh, it's gonna be 50 from the x component, and then that's where you want to your calculator. So, well, or in my case, MATLAB. Okay, so the 2.9. Okay, so in that case, if we draw the situation, so we have the ship 50 miles an hour, and the passenger 4 miles an hour. So yes, so because the passenger is, instead of going against the ship like in the previous one, is kind of going with it. The passenger speed relative to the surface of the water is greater than that of the ship itself. It's kind of like if you're on one of those moving walkways in an airport. Not to New Orleans has anything like that, but so if you're on the walkway and you're walking yourself, then the velocity vector for the moving walkway and your own from you taking steps will add together, so you're going faster. Okay, and then for the direction, so the tangent's going to be equal to 4 okay, over -25 square root of 2. The x component is still negative, so we're gonna have to add pi to that. So since the angle of the ship is 3 pi over 4 or 135 degrees, you can see from the picture here that the angle for passenger is going to be the resultant is going to be a little bit less. Oh, yeah, it is just slightly less. So it's roughly 152 degrees. Thanks. This is not really scale, but passenger going only 4 miles an hour, this vector is gonna be even smaller than this. Than what's shown here. Okay. Any questions about how that worked out? Okay. Any other ones that are raising your stress level going into a final? Number 5. Okay. The work one. Okay, so what you're given here is you have a force vector F. And it's written IJK form, but I don't like writing it that way. 3 minus 4, 1. And that is applied to move an object along a straight line. So the object's initial point is 1, 1, 0. 2 is its final destination. 5 minus 2, 3. Okay, forces in newtons, and units of sorry, about meters. And that's for what is the total work. So what you do is first thing, from these two, you subtract them to get the displacement vector D. So we subtract the components. 4 minus 2 minus 3. 3. Okay. Now, there's still work being force times distance, where the force is whatever is applied in direction of motion. So the magnitude of that component of the force times the distance. So the way it was derived is magnitude of the force times the distance times the cosine of the angle between them to account that the force and displacement are happening in different directions. But you don't need to really do any of that. That's just for dot product. So that is what you do. So you have 3 minus 4, 1 dots. 4 minus 3, 3. So you multiply corresponding components. And add it all up. And that's it.
Is that a Newton meter?
Yeah. Speaking of dot product and its close relative cross product, considering at maybe scope a number of problems, using quite a bit this semester, but formulas for the dot cross product are on the formula sheet. Please don't add to my collection of gray hairs by messing up those operations. When dot products a number, cross product is a vector. Someone's gonna do it, but I had to ask them.
So, on number 8, like when you're finding the volume of the parallelepiped.
Yeah.
How do you know, like, how do you know which ones to do cross product and which one is?
It actually doesn't matter.
I did it wrong, because when I use something else, like use ones other than what you did on the. Other than what you did, I got a different answer.
Because another way to think about this is, if you took all three vectors and stacked them in a matrix, what you're computing to get to volume is determined to that matrix. If you applied the operations differently, in terms of what's the cross product versus the dot product, that is a tantamount to rearranging the rows of a matrix. And those of you who've taken linear algebra, when you rearrange the rows of a matrix, what does it do to the determinant?
Negates it.
It negates it, but the formula for volume calls for absolute value of the determinant. But yeah, it is. So somebody must have gone awry there. It seems to be most common mistake I see, like by multiple people, like enough to stand out, is that second component of the cross product, how you get to yeah. Multiply things a little differently, but
Just forget the negatives that you have to put in.
yeah, and it's a good idea, time permitting. When you're taking a cross product of two vectors, go ahead and take a dot product of your cross product with one or both of the vectors. Is it zero? Supposed to be dividable to both of them. If not,
That's good advice.
yeah, if not, you know, you messed up.
Like, the factors.
Yeah,
Yeah, that's,
but yeah, we just most of the time stick to the very first one.
yeah, because it is a determinant, it's a set here, but with a very strange first row. Okay. Any other problems to go through? I was happy, probably like, please, no one say anything. That's how I'm at faculty meetings. Professors want to talk. Yeah. Certain problems will involve integrals because of computing arc length. There'll be nothing nastier than U substitution required.
I know this is like a long shot, but will you have the key to the practice before the exam?
But the keys,
Oh, it is? I didn't see it.
Yeah, they were posted together.
But, oh, I didn't see it. Well,
Okay. So no, it wasn't a long shot. Um, um, Yeah, when I was taking the final, one of the integrals turned out to be like big substitution, then secant cubed. I was like, oh my God, don't come after me for that one. So I changed it. Sorry. Questions from the online crowd?
$14.
Okay. Oh, they're up, arc length one. Okay. So. Alright, so Kermit's question is, find out a doable integral. Six plus 1 over 2x, so this y is a function of x, where x is between 1, 2. So the arc length formula for this kind of curve is integral over both x values from 1 to 2, then square root of 1 plus y prime squared. Okay. What is y prime? In this case?
X squared plus -1/2 x to the -2.
Yeah. Okay. All right, so now we fill that in. Square root of 2 minus 1 over 2x squared, the whole thing squared. These algebra alert. Okay, so then you have x to the 4 over 4, and then minus twice this times this. Then plus the last term. Yeah. Okay. And then when simplified, cross term, we have the x squared is canceling out, and we have so minus 1/2. Okay. Now, that looks pretty hopeless until you take these two constant terms. I'm going to put this in parentheses to help you see what's going on here and how this problem is crazily contrived to be doable. So you combine those two constant terms. So now you have the 1 minus half gives you plus 1/2, or plus 1/2 plus 1 over 4x 4. So the key here is, if I look at this in parentheses and compare it to what we have here, the only difference is that middle term has a different sign. Now, this is a perfect square. Square of this. So if all I do is change this to have change the sign of that middle term, that is also a perfect square. But a perfect square of what? Yeah. So we have x squared over 2 plus 1 over 2x squared squared. Okay, but now we're taking the square root of the square. Okay, so this happens in a number of problems where whoever's writing a problem tries to make something work out nicely. And that is, something happens to tweak a perfect square. So we're trying to change a minus b squared to a plus b squared, or vice versa, because The only thing it changes is this middle term here. So the y, and therefore the y prime had to be contrived so that the central term in this expanded perfect square is equal to -1/2 times this +1 here to make that happen. Well, questions up to this point?
The square root.
What?
What happened to the square root?
Oh, well, it's square root of something squared. So maybe they cancel each other out. For an arc-length problem, just to make it doable, certain things have to happen. One is either perfect square chicanery like this, or trig identities, cosine squared plus sine squared equal 1 coming to a rescue. Or maybe something can be done by use substitution. After factoring something from out from under a square root sign. Hand to hand. It has to be something like that, or we just won't be able to do the integral. I have had colleagues who'll do that. They'll put an integral on an assignment, or whatever, that really is impossible and not tell our students. Yeah, so. Okay. Now let's take a look at this expression right here that now needs to be integrated. If you consider where this simple expression came from, it turns out that we actually can see from what's written on the board what the antiderivative is going to be with very little work. Yeah, so because this expression of a minus in the middle came from taking a derivative of this. Now we have the same thing except with a plus in the middle. So if we're going to anti-differentiate this, we're going to wind up back here with the opposite sign in the middle. So it's going to be x cubed over 6 minus 4 over 2x. And then you plug in limits 1 and 2. Yes. You know it well. Definition of a sum into a problem is a pretty decent approximation to a square root of 2. Anyway. Okay, so are there any questions about how that one played out? Problem 15, exact same trickery with perfect squares. This with a different function. So, yeah. Any other problems we're looking at? So over 20 problems, if you get 15 problems totally right, then you get an A on the final. Because each one is worth 6. So, but make sure you pace yourself responsibly, like don't get caught spending way too much time on one problem out of 20. If it's giving you fits, move on. It's, you have wiggle room to ditch a few problems altogether, if need be, and then come back to it if you can. I guess it kind of hit hard of arc length, for free arc length problems, something's.
And it's a good thing we're all, I imagine we're all pretty good at arc length then.
Yeah, yeah, you still have a lot of practice in the homework.
Did you, I mean, can you show how you did the integral on number 20?
20. Oh, okay. Okay, so this is arc length of a polar curve. By R equals secant theta. Theta is between 0 and pi over 4. So the arc length formula for this case is integral over your theta limits of square root of r squared plus the r d theta squared. Okay. So fill in, well, what is r d theta in this case?
Is it tangent?
Okay, so now fill in all that. So we have secant squared theta plus secant squared theta tangent squared theta. Okay. Now, we have under the square root sign, we have a common factor of secant squared. So we go ahead and, whoops, I forgot to throw in that. So I can factor out secant theta from under the square root sign. And then what's left is still 1 plus tangent squared. Anyone tell me what is 1 plus tangent squared? That is secant squared. Now we have another factor of secant after we take the square root of that. Now we have secant squared theta d theta. Okay. But then this is one of the fundamental differentiation rules for trig functions. Secant squared is a derivative of tangent. I'm not sure if that's what you're asking about or something else. You've forgotten that rule, or
I don't really know, I didn't share rules because they just didn't teach me to.
oh, whoops.
Yeah, my high school had a really crappy trig class. It was basically half trig, half something else.
Oh,
So-
well, I guess this would be the
Breakout trig?
No, it wasn't even trig, it was called Advanced Math Plus.
Wow,
That's pretty big.
advanced
But
math.
I guess this is really a failure not of a trig class, but a calculus class.
It was like a prerequisite to calculus, so it only taught you like the bare minimum of trig and then kind of moved on.
Okay, but
They're kind of easy to forget, so I'll use them.
so we didn't tell you all 6 of these.
I know those,
Okay,
yeah. I
Oh.
just didn't know the 1 plus tangent squared would give.
Oh, that, okay,
So I
yeah, I wasn't sure what part of the
asked.
problem was
Yeah.
causing trouble. Okay. All right, never mind then. Okay.
So would that be like on the front of the sheet?
Oh, thanks, I'm on there now, although it might not, I'll just go back and look and see what's needed. Yeah, because I mean, the integrals would be of a different character. I'll check.
Okay, I have a really silly question.
Um,
Okay, this is silly.
Okay,
It has-
thanks.
It has to do with the unit circle.
Okay,
So. I know the unit circle, like. But when it comes to making the triangles out of the unit circle, my brain is so confused, like I'm making the triangles.
okay,
So can you do like, for example, do just like make the triangle out of 330 degrees?
okay, I'm not sure if I understand what you're asking.
Like how do you derive the value?
Yeah,
Like instead of the burns.
Oh,
Okay.
1, 2 squared root of 3.
Yeah. Okay, so
This is silly.
330 degrees,
Huh?
330 degrees?
Yeah.
Okay,
Like one of the, not, yeah,
yes, something outside quadrant one.
yeah.
Okay. Um. So that's where the symmetries have to be taken into account. That you're gonna figure out what it is for, so in other words, you're trying to get sine and cosine of 330 degrees. Okay. Okay. Okay, but to help with that, you'd be looking at. At 30 degrees. Because what you can see here is that the cosine will be the same. And what about the sine?
That'd be negative.
Yeah. So really, you're always gonna be going back to quadrant one, seeing which symmetry you're going to apply based on where you are in a circle. Like which quadrant, you're in.
So I mean, like, so when we make a triangle and
Wait, I need to identify this angle more carefully. Okay,
okay, so then you say like I just feel so silly. I just figure.
Do you mean like the ratio
Yeah.
square root two?
Yeah,
oh, okay, as far as, yeah,
exactly. The values for each angle. That's what she.
okay. Yeah, I had a friend who, when she was a math student, went on to become a math teacher, she would, put something on the steering wheel of her car that had all the cosine and sine values, so they're always in front of her every day, so.
Cause we, theoretically add that to the cheat sheet as well.
If it's needed for an answer, yeah.
You already gave me one long shot. I know that's a
Okay.
big ass.
Okay, so. And it's really what it amounts to, because the numbers, it's easier to work with the numbers involved if you think of whatever square root of, because you think of these, the three main angles from quadrant one. So the values you're dealing with are, so in the case of sine, you have square root of 1/4, square root of 2/4, square root of 3/4. But then they'll simplify to the familiar 1/2 square root of 2/2, square root of 3/2. I guess I keep coming back to like when I'm trying to figure stuff out, something like that. Just remembering what is 4 quadrant 1 angles. So I guess to work with these fairly efficiently, there's still at least a certain amount of memorization involved, not too much. Like, I definitely would not rattle off the top of my head, cosine or sine of 330 degrees or 315 degrees. Well, I'd have to think about it a little bit. Just nothing else to make sure I got the sign right. I actually try not to deal with angles that are greater than pi or 180 degrees. I'd rather work with negative angles in that case, because you also have a relationship that when you negate an angle, the cosine doesn't change and the sine negates. So the even and oddness comes up all the time. As far as answers go and such, I perfectly fine with you since, I mean, you're allowed to use calculators, can just do everything in decimal. And, like if you have, like for instance, if a problem with a ship and the passenger, depending on the directions, the numbers don't work out nicely, then you might as well just turn to your calculator to get the magnitude and also get the angle. I mean, you'd have to in that case. Whereas the actual problem of practice, it could be done where things work out more nicely because the ship and the passenger going in opposite directions. But if you work things out in decimal form, I'm not going to care. So I'm going to have all the different forms of the answer to look at anyway to compare. Radians versus degrees, if I don't specify, it's because I don't care. I'm interested in, do you know the right formula to use for a certain situation for the various problems we had, angle between vectors, distance from a point to a plane, things like that. But I'll give the real final one more look and see if there's anything else that needs to be added to the formula sheet. And if so, then get a notification from campus. Still 15 minutes. More.
Determining the intervals for 19, like,
Oh, okay. Well, as far as the interval, in this case, it's not an interval needs to be determined because the interval itself is given. Like your,
yeah,
um,
well, okay, you have the cosine 2 theta is 0, like from 0 to pi,
yeah,
but it's doesn't,
I'm sorry, what?
I mean, cosine 2 theta doesn't equal 0.
Yes, it does.
Because, yeah, if you plug in 0, you get 0, wait.
No, that's cosine. If you plug in pi over 4, then you get 2 theta pi over 2 with cosine at 0 there. Okay. Well, to highlight what was written up for that problem, it's helpful to keep in mind when just plain old cosine and sine are 0. So the sine of different variable, sine t equals 0, if t is k times pi, where k is integer, whereas cosine of t 0, if t is equal to pi over 2 plus k pi, where again k is an integer. So if you have cosine of something else, you want to know where that is 0, equate that to t. So for cosine of 2 theta, equals 0, then think of two theta as your t. So two theta is pi over 2 plus k pi, but then you want to know what theta is. So theta is going to be pi over 4 plus half integers times pi. So then what you would do is start plugging in values of k, starting k equals 0, 1, 2, until you wander outside of your given interval. So in this case, if theta is between 0 and pi, then you're going to use this formula for k equal only to 0 and 1. Because anything past that will put you outside the interval. But these are well worth knowing. Find out when certain cosine or sine based functions are 0. And when you have cosine of or sine of k theta, where k is greater than 1, that compresses the graph. So those whatever factor you multiply your angle by in a sine or cosine, the larger it is, the more roots it'll have.
I just think of it because I think of like if you plugged in pi over 3 for theta, it'd be cosine of 2 pi over 3.
Right. Yes, it would be.
And it would be 0. But like,
I wonder if something's getting reversed in your head.
yes, it just doesn't really, it just doesn't make sense when I think about it. But I know that
For example, if you're thinking in terms of, say, okay, well, let's try this, like it's thought experiment, if you will. Let's say we let the theta be 3 pi over 4. But then you're taking cosine of 3 pi over 2. And the fact that, is it the problem of the fact that that is outside of this interval? That what's causing difficulty? Yeah, and the thing is, 2 theta is allowed to be between 0 and 2 pi. So so the other thing that's going wrong here is that you're applying the restriction at the wrong time. It doesn't matter what we're taking the cosine or sine of, it's the original expression that has to satisfy this condition. Whatever's done to it before you take a sine or cosine, it's not part of this. But yeah, I mean, these kind of problems are full of brain traps like that. Make you wonder what's wrong. Although it can be, it seems cumbersome to bring additional variables into it, like think to a sine t or cosine t. But since sine and cosine, like ordinary sine and cosine, are so much easier to work with, like we can possibly remember things like this, just from the original version of a function. Then by making kind of associations, we can see what's happening with this one. And it's always, it can be helpful to try, if it's possible to work things out in an algebraic way, because then it's even if your brain's having trouble wrapping your head around it, presumably the algebra won't lie. Okay. Anything else in the last few minutes of the semester?
So if there's a common factor inside a radical, you can just take it out.
Well, if it's squared onto a radical. Yeah, so it's like if you have x squared onto a radical, but you can take it out as an x.
Oh, because it was secant squared, so we took out the secant.
Yes.
Okay.
Yeah. Oh, I guess that's it. Till Monday.
It's been a pleasure.
Right.